what we concluded in the previous video as applied to where dynamic programming is applied to problems that involve successive subdivision. You begin by thinking what the decision that has to be made is in the top level piece of the puzzle. So in a matrix chain multiplication, where to put the outermost parentheses. Then you need to ask what subproblems would have to be solved to figure out how good your choice is. So the choice was where to parenthesize in our example. And the subproblems are how to parenthesize the resulting submatrices. That's recursive, but also you need to know how to multiply the two groups of matrices. That is to say, how much it costs to multiply the two groups of matrices. For example, the matrix A1 and the matrix A2 ... That pair of matrices have to be multiplied, and there's a cost to that multiplication. Or, had you parenthesized differently, the matrix A1 ... has to be multiplied by the matrix A3 ... So then we need a formula for the combination work that when coalescing the parts. In our example, we have to coalesce A sub I ... k and A k plus 1 ... j to form A sub I ... j. And we know that A sub I ... k is P sub I minus 1 by pk, and A sub k plus 1 ... j is pk by pj, and thus the combination work is the product of P sub I minus 1, P sub k, and P sub j. Then you need to write down a formula for the goodness of the best choice of your decision. So in our example, that was M sub ij is the minimum over the breakpoints of the expression inside parentheses. Then you need to arrange the subproblems in order from small to large and solve each one, keeping track of the solutions for use when needed. We need two tables, one telling the value of the solution to each subproblem, we called that M, and the other telling you the particular option you chose for the solution to each subproblem, thereby giving the schedule for solution. Program is simply a copy of that given in the previous slide, previous video, for producing the schedule for the matrix chain multiplication problem. We now move on to another dynamic programming problem that also involves subdivision choices, both to get more practice with the idea, but also to figure out some further commonalities between this problem and the one that we analyzed before of matrix chain multiplication, as well as some differences. The problem is how to optimally fill a convex polygon with triangles. We'll define the term convex polygon shortly, but here we have a polygon that is divided into triangles in two different ways. And the problem that we want to solve is which division into triangles is better according to a measure that we will talk about shortly. This is not immediately, obviously, a successive subdivision problem, although it clearly involves multiple subdivisions. In some sense, we need to make those lines that form the sides of the triangles, choose them one at a time. But first, we need to define some terms. A polygon is a piecewise linear closed curve in the plane. We form a cycle by joining the line segments end to end. The segments are called the sides of the polygon, and the endpoints are called the vertices. So the endpoints are the heavy dots, the vertices are the heavy dots, and the lines between them are the sides. It is defined to be simple if it does not cross itself. That is to say, the edges do not intersect one another except two consecutive edges sharing a common vertex. So the upper polygon is not simple. The lower one is. Its edges do not cross each other. A simple polygon defines a region consisting of the points it encloses, the interior of that simple polygon. The points strictly on the outside are the exterior, the interior are strictly on the inside, and the lines themselves form the boundary of the region. A simple polygon is said to be convex if given any 2 points on its boundary, whether or not they're vertices. The line segment between them lies entirely in the union of the polygon, that is to say the boundary, and its interior. Convexity of a polygon can also be defined by the interior angles. The interior angles all have to be at most 180 degrees. Note they can be equal to 180 degrees and still satisfy the definition of being a convex polygon. Our problem is to fill a convex polygon with triangles in such a way that some measure of the triangles is minimized. Let's say we have a convex polygon and we want to describe it in detail. So let's describe the list of vertices, positions, and give those positions in counterclockwise order. We'll pick one of those vertices, we'll call it V sub 0. Let's say it's the leftmost vertex in the diagram we see here. And then the next one around, in this case, to the lower and right of that one will be V1, and the one after that V2. And we'll go all the way around to Vn minus 1. And then Vn minus 1 will be attached back to V0. So now the lines V connecting one vertex to another are chords. And we can describe that as by the ij that are the 2 points being connected. These chords will lie entirely on inside the vertex, inside the object, except for their endpoints, unless the two, the I and the J are adjacent modulo n, which is the number of sides. We carefully define a triangulation of a convex polygon as a maximal set of chords. A maximal set is a set such that every chord not in that set intersects one of the chords in the set, in the interior. Such a maximal set subdivides the interior of this polygon into a set of triangles. That set is a triangulation. There are exponentially many triangulations of an n-sided polygon. In our particular problem, we will consider the measure of a triangulation, the sum of the perimeters of its triangles. And then our problem is recast as find that triangulation which minimizes this sum of perimeters. To do that, we need to talk about a triangle in terms of the three vertices that are the vertices of the triangle, the three polygon vertices that are the vertex of the triangle. So the triangle V sub I, V sub j, V sub k is a triangle, and its weight is the perimeter. That is to say, the sum of the lengths of its sides, and its sides are the VI VJ side, the VJ VK side, and the VK VI side. A property of triangulations of a convex polygon with n vertices is that every such triangulation has n minus 2 triangles and n minus 3 of these interior chords. We'll not prove that right now, but later we will see an interpretation of a triangulation as a tree, and the property will fall out of that interpretation. let us move on to formulating the dynamic programming solution that yields the triangulation. So we are searching for a minimum weight triangulation for the polygon whose vertices go from 0 to n. But in order to keep the structure of this problem as similar to the matrix chain multiplication problem, we'll refer to a polygon that goes from 0 to n with the subscripts 0 plus 1, that is to say 1 to n, and in general we'll refer to a subpolygon as which in the example here goes from v sub 1 to v sub 5 and then connects back along a chord. We'll refer to it via the indices, the first vertex index plus 1, 2 to 5. Okay, so even though the polygon marked in color here goes from v sub 1 to v sub 5, we'll refer to it by the indices 2, 5. Our problem is to subdivide the polygon. Initially, the full polygon, that we refer to by v sub 1 to v sub n, with v sub n being v sub 0. We want to divide that polygon with a chord into two subpolygons, and the issue is how to produce those two subpolygons, that is to say, which chord to choose. If we choose a particular chord, we can, in a recursive fashion, determine what the minimum weight triangulation of each of the subpolygons that are thus formed. For example, the subpolygon marked in color, which we're calling the subpolygon that is indicated by the indices 2 to 5 and thus involves vertices 1 through 5. We want the minimum weight triangulation of that, and we'll be able to do the same with the other subpolygon. That's the complement of this one. We hope we will be able to compute m sub I comma j for all ij where I is less than or equal to j. If we could do that, then we could use our small to large organization to ultimately be able to compute m sub 1 comma n, that is to say, the weight of the minimum weight triangulation, and that would yield the associated t of 1 comma n, which is the full triangulation of the polygon. We also note that if we look at m sub I comma I, that's the triangle, the polygon if you will, that goes from the I minus 1th vertex to the ith and back. And that's a line segment, namely the line segment v sub I minus 1 to v sub I. This is a trivial polygon. It has no area. Moreover, it has no contributing triangles whose perimeter we want to count. Thus, we can say m sub I comma I is equal to 0. We are going to consider the subdivision as follows. To consider the total the triangulation of a subpolygon that goes from v sub I minus 1 to vj, we will introduce a triangle that goes between this chord, v sub I minus 1 to vj, in the example, v sub 1 to v5, and any one of the other vertices in that subpolygon. So it could go to v2, v3, or v4, k equals 2, k equals 3, or k equals 4. We will, in this example, k is 3, and we have the triangle that goes, is the v1, v3, v5 triangle. That triangle has a perimeter. It's what we call W of v sub I minus 1, v sub k, v sub j. That is to say, in the example, W of v1, v3, v5. It also subdivides this subpolygon into two additional subpolygons that go, in this example, from 3 to 5, in general from k to 5, and from I minus 1 to k, the two narrow lines that you see, bound polygons that go v1, v2, v3, happens to be another triangle but need not be in general, and another polygon v3, v4, v5, likewise another polygon. The result is that the total perimeter m sub ij for any given k is m sub ik, the total weight of the polygon that goes from vertex I minus 1 to vertex k. Another one, which is m sub k plus 1j, the total weight of the triangulations making up the polygon that goes from vertex k to vertex j, plus the triangle, plus the perimeter of the triangle we introduced. That W of v sub I minus 1, v sub k, v sub j. So the idea then is choose a particular k that subdivides this polygon. Doesn't that sound just like the splitting problem that we had in the matrix chain multiplication problem? Is that we can take the same algorithm that we use to minimize this, to set a schedule or to set the subdivisions, that we used in the matrix chain multiplication problem. The only difference of this algorithm is the term that's added in the innermost do loop to the sum of the two component m values. Here it's the sum of perimeter of that particular triangle that was produced by the subdivision. This problem of triangulation requires the same algorithm for subdivision as the matrix chain multiplication method did, albeit with a different combination cost. But it is actually a little bit simpler than the matrix chain multiplication cost, in that the array S itself here yields the triangulation that we needed, and we're done. Whereas in the matrix chain multiplication problem, we needed to use the schedule array S in a further calculation that actually multiplied the matrices together. We now consider an alternate interpretation of the polygon triangulation problem that will illuminate the problem and also yield an interpretation, a proof of the lemma that we needed. Consider the triangulation in the middle of this diagram. It consists of a series of triangles, each with 3 sides. Some of the triangles have 3 sides that are not polygon edges. Some of them have 2 sides that are not polygon edges. And some of them have 1 side that are not polygon edges. In any case, let us consider a graph that we'll call the dual graph of the triangulation. The nodes of the graph are going to be the triangles. So we will have a node, if you will, in the middle of each triangle. And the arcs of the graph are going to be determined. They'll connect any pair of triangles that share a triangle side. So, for example, in the dual tree to the triangulation in the middle, the dual tree shown on the right, the big triangle is a node which has 3 sides, none of which are polygon edges, and so it has 3 other triangles as its neighbors. That is to say, there's an arc between its node and those other 3 nodes. If we look at the triangle to the left of that largest triangle, it has one edge that's one side, that's a polygon edge, and 2 other sides that are shared with 2 other triangles, and thus it's got arcs to 2 other triangles. And if we look at the triangle in the top right, we see that that triangle has sides that are 2 sides that are polygon edges, and only 1 side that goes to another triangle. So it has just a single arc in the graph connecting it to another node. This graph, we call the dual graph, can be shown to be a free tree, and this can be seen in the next slide. We are going to augment our tree. First, it can be shown that there must exist at least one triangle in the triangulation that has two polygon sides, two polygon edges as its sides. Let us call the vertex between these two sides v sub n minus 1. And it, as a polygon, has polygon edge comparing vn minus 2 to it and v0 to it. That is to say, it is the triangle v0, v10, v11 in this example, v0, vn minus 2, vn minus 1. Okay, so we have chosen that triangle, called its vertex vn minus 1. That triangle has only one side that is adjacent to another triangle. Let us consider the node for the triangle with two polygon edges as sides. Call that the root of a tree. And let us consider it to have two children, one of which is its connection to the adjacent triangle, but the other of which is attached to a new type of node, which is a polygon edge a sub n minus 1, that is to say a sub 11 in this example. So we have a root and binary connection. Now consider the one non-polygon edge node of this root. It corresponds to, in this example, to the triangle V0, V1, V10. That one has, in this example, a child, a single other child, or a single other connection than the one already discussed, and we'll have a new edge-type child, a sub 1. We keep repeating this process as we go down the tree, and what we see is that we end up with a binary tree whose leaves are a sub 1 through a sub 11. That is to say, this binary tree has n minus 1 leaves. But there's a theorem about binary trees that a binary tree with n minus 1 leaves has n minus 2 internal nodes. But the internal nodes here correspond to the triangles, and therefore we know that there are n minus 2 triangles. Moreover, since each internal node, other than the root, has one edge in the graph entering it, there are n minus 3 edges between the internal nodes. That is to say, there are n minus 3 chords. Based on this tree interpretation, that the triangulation has n-2 triangles and n-3 chords. But let's go back to this tree interpretation of the triangulation, the so-called dual graph. Each triangulation will have a different dual graph. And so an alternative view of the triangulation problem is that we're trying to find the optimal dual graph. That is to say, the optimal tree formed as described. Now let's remind ourselves that in MCM, in the matrix chain multiplication problem, the schedule that we produced yielded an evaluation binary tree, with the leaves being the individual matrices. This is the same as what we saw in this triangulation problem, except here the leaves are the edges, well, all but the closing edge, v n-1 to v0. So the matrix chain multiplication problem can be thought of as producing an optimal evaluation binary tree, and the triangulation problem can likewise be so interpreted. We are now finished with problems that have the subtype successive subdivision. We have seen that they can each be interpreted as finding an optimal binary tree corresponding to the subdivisions, and that the problems are solved in schedule, small scale entities to larger scale entities. In the other type of problem for which dynamic programming is appropriate, the problems consist of steps in a sequence and a situation in which at each step we have to make some choices. And we want to optimize some property of the overall sequence. The example we gave before was two parallel assembly lines in a factory. We'll call them lines 1 and 2, and we'll let the letter I indicate which line we're talking about. Each line will have the same number of stations n, and we'll name the stations of the first line S sub 1, 1, S sub 1, 2, ... to S1, n. Similarly, the second station will have, the second line will have the same n stations, or will do the same tasks, but those stations will be named S sub 2, 1, S sub 2, 2, up to S sub 2, n. As I've said, for each station, for each j, S sub 1j does the same thing as S sub 2j, but they each have their own times for completing the task, and we'll let A sub ij refer to the time taken to do the task at station S sub ij. We are given the A sub ij's. Moreover, at every station, in this example, we can either stay on that line or transfer away from it. And if we transfer away from it after stage J, we're going to move from stage J to stage J plus 1 and switch lines from I equals 1 to I equals 2, or from I equals 2 to I equals 1, and we'll let the switch times be t sub ij. Okay, so that t sub ij is the time for when you're at stage J and moving on to stage J plus 1, of switching from, if I is 1, from 1 to 2, or if I is 2, from 2 to 1. In addition, there is an entrance cost for each of the two lines, E sub 1 for line 1 and E sub 2 for line 2. And likewise, there's a cost for taking things out of the respective lines at the end, and we'll call exiting the cost for exiting, or the time, if you will, for exiting from the first stage x sub 1, and the time for exiting from stage 2, x sub 2. The problem in this type of situation is not where to subdivide. There's already a subdivision. It's between one step and the remaining steps. But the problem is that for each step, we have to decide what that step will be. And the challenge is that the overall global solution will depend on the whole sequence of decisions that we make. So whether we want to exit, for example, from station S sub 1n or exit from S sub 2n doesn't just depend on what x sub 1 and x sub 2 are, or on what the time a sub 1n and a sub 2n are, but also in the times that it took to get to those respective choices. And those times that require an optimization of what goes before the nth stage. We take this dynamic programming to pick some convenient stage of the process. I've just given you the example that we might pick just before the last station. And then we have to decide whether that last station should be S1n or S2n. That is a simple binary choice. What do we need to know to decide which options are better? Well, of course, we need to know what the fastest times are for S sub 1n and S sub 2n. But those times consist of both information at those stages, namely the A sub 1n and A sub 2n values, and as well as the exit times from those stages. They depend not only on that, but also the times for getting to S1n and S2n, respectively. What we can see is that getting to a given station ready to execute its task, the fastest of those will be the minimum of staying on the same line and getting the fastest time through that line, that previous station, including its own time. The minimum of that, or if you wanted to not stay on the same line but switch lines, it's the fastest time through the previous station, but on the other line, together with the time it takes to switch lines. So now we have a recursive statement where for one line we get its total entry cost to be the smaller of a line before it, where the line before it can either be on its own line or on the other line, in which case a switch is needed. State this recursive process mathematically. Let's define f sub I of j to be the fastest possible time to get the object we are manufacturing through the ith line, the j stage of the ith line. So at the beginning, to get through the first stage of the first line, that's f sub 1 of 1, the time required is the entry time, E1, plus the time taken at the first stage of the first line, A sub 1, 1. Similarly, for the second line, f sub 2 of 1 is the entry time, E2, plus the time taken to get through the first stage, A sub 2, comma 1. The f1 and f2 of j for j bigger than 1 are each a minimum that was discussed on the previous slide. They're the minimum of staying on the first line, f1 of j, when you stay on, the time that it took to get through the j minus 1 stage, plus the time at that new stage in that line, A sub 1j. That's one of the terms. The other option is that you were at stage j minus 1, you were on line 2. And so the time through that was f2 of j minus 1. But then you had to transfer from 2 to 1, from line 2 to line 1, which takes time t sub 2, comma j minus 1. And then, as well, you need to do the job on stage 1, the time requiring the time a sub 1, comma j. F sub 2 of j has a similar analysis. You can come from line 1, in which case you've gone through f sub 1 of j minus 1. Then you have to transfer from 1 to 2, from line 1 to line 2, which takes t sub 1 of j minus 1. And then you have to actually operate on stage, at stage 2, which takes time a sub 2 sub j. Or alternatively, you were already on stage 2 and you went through ended up on stage 2 at stage j minus 1, which had time f2 of j minus 1, and then you continue on stage 2 a sub 2 comma j. The total time at the very end is the minimum of f1 of n, that is to say you went through the system and ended up on line n and you exit on line 1, so f1 of n plus x1, or you ended up at stage 2, your f2 of n and x2, and it's the minimum of those. This is the algorithm implementing that. We simply initialize for j equals 1 and pass through the stages one by one from stage 2 through stage n. There is an error, I believe, in this statement of the algorithm. The subscript on L, the 1 subscript and 2 subscript respectively, should be deleted and simply should say L of j in all cases. In any case, this L array stores the result of on which line you're going to do stage j. So there's a loop over the stages, and then when you finish, you are at f, you have the values of f1 of n and f2 of n, and this final check outside of the loop is to add the last stage and record whether we end up coming out of line 1 or coming out of line 2. There's only one loop here, the j equals 2 to n loop. The algorithm is thus theta of n. So, we have solved the assembly line problem as an example of this decision at every stage procedure. Most problems for which you will want to use the dynamic programming paradigm to solve will be in one of the two forms you've seen. The first, where you have to make subdivision decisions at each stage, and the other in which you have a sequence of steps and have to make choices at each stage. Another example of the latter type of problem is the problem posed at the beginning of the previous video, where you have two parallel polygons and you want to tile between them with triangles in such a way as to minimize their total area, and where you're given one initial top vertex to bottom vertex connection. In this example, let us assume that we're given the line connecting vertex 0 on top to vertex 5 on the bottom. The decision at that point then, if we're going to move counterclockwise, is whether to move from vertex 0 to vertex 1 on the top, or to move from vertex 5 to vertex 6 on the bottom. If we take the move on the top, we form the triangle whose sides are 0 to 1 on the top and their respective connections to vertex 5 on the bottom. And we create a new line connecting 1 to 5, from which we can then proceed. If, for example, we then at the next stage decide to move along the bottom, we will move from 5 to 6 on the bottom and create the triangle with the 5 to 6 on the bottom as one of its sides and the lines connecting them to 1 as the other. So each stage forms a triangle, and in this example we move also along the bottom for the next stage, going from 6 to 7, also along the bottom at the next stage, going from vertex 7 on the bottom to 8 on the bottom, moved on the bottom again for the next stage, going from vertex 8 to vertex 0 on the bottom. Then we decide to move along the top from vertex 1 to vertex 2, and so on until we come back to the line that we started from. The idea is to make these choices in such a way as to minimize this global property of the area of all the triangles in question. Notice that the total number of stages is going to be the total number of line segments around the top polygon plus the total number of line segments around the bottom polygon, because at each stage we move along exactly one of those. Most problems, these problems that involve choices as sequence of steps may not simply involve binary decisions at each step. In our two examples, it has been binary decisions. In the assembly line problem, we had the decision of whether to do the task at stage 1 or do the task at stage 2, a binary decision. Do the task at line 1 or do the task on line 2, a binary decision. Here, with this sort of cylindrical tiling problem, we have the binary decision at each stage whether to move along the top polygon or along the bottom polygon. But in many problems, the decision is not simply binary, but may involve more options. So, for example, you might have to choose among 3 options at every stage. Nevertheless, the basic form of the problem and its solution is the same. As I said in the beginning of the first video, the use of dynamic programming is when you have an optimization problem, a problem that involves optimizing some global property. So the time to multiply a bunch of matrices together, or the time to produce a product on an assembly line. Those are both examples of a global property that we're optimizing. And then we want to find an algorithm that produces that optimal property, produces that optimum. In some such problems, for the global problem to be solved optimally, the sub-problems in which we divide it, each should be solved optimally. But this is frequently not the case because of the relation that we have of one subproblem to another. It's often the case that being less optimal on one stage, we may make a big savings on another stage, or in the case of subdivision, being less optimal on one division, we may make a big savings on another division. Matrix chain multiplication, in fact, satisfies this principle of optimality, but not generally the case. Another thing that should be realized in regard to dynamic programming applicability to optimization problems is that there exist problems which are themselves necessarily exponential in N. Such problems are called NP hard. We'll define that carefully later at the end of the course. But in any case, these are optimization problems that can be formulated to be dealt with by dynamic programming. It's just that for these problems, the result of the dynamic programming formulation is itself not efficient. That is to say, its solution is takes exponential time. Ideally, the number of subproblems should be at most a polynomial order, and we've seen in the matrix chain multiplication situation where we had polynomial order, that is to say, order n cubed performance, and in the matrix chain multiplication, order n performance of the dynamic programming scheduling. But for these problems that are essentially exponential, we can't achieve that even by the dynamic programming paradigm. We have now come to the end of the lecture part of the presentation. Here we have a worksheet. You need to answer these questions on the worksheet, and as usual, pass them in, and in time for the class in which this video is due, which is next Thursday. This video ends with two exercises. At the moment, neither of them is fully specified here on the video, and the full specification will be made on the Sakai site. The first exercise has you trying the triangulation on a very simple case of a convex quadrilateral. The second exercise involves having an object in an image and being able to walk around it as close as you can to its boundary, assuming that at every position in the image you have a measure B that says how boundary-like that position is. The idea is you want to walk around and stay on places that are more boundary-like than alternative positions that you might walk around on. The problem also involves a constraint of staying at least a certain distance from the center point of the object, which is already going inward. And at every stage you have the choice of moving along at a distance from the center that you're at, or of going a centimeter inward and then moving along at that distance, or going a centimeter outward and moving along in that at that distance. This problem falls in the problem type of a sequence with decisions at each stage, and there will be a bunch of questions about how to design the dynamic programming solution for this problem, and those questions will appear in the Sakai document. This ends the series of 2 videos on dynamic programming.